In this lesson, we'll look at complex numbers. In particular, we will simplify imaginary numbers, write complex numbers in the form of a plus bi, and then perform operations with complex numbers. To start with, we have the definition of an imaginary number. An imaginary number, I, is the solution to the equation x squared is equal to negative 1. As you know, anytime you square a real number, you always get a positive. So mathematicians ask, well, how could we square something and get a negative? There are no real numbers that we can square and get negatives, so we created this extension and we call them imaginary numbers. As such, we know that I, the imaginary number, is equal to the square root of negative 1. And since this I number is the solution to the equation x squared equals negative 1, we must have that I squared is equal to negative 1. One more little fact about imaginary numbers. If b is a positive real number, then the square root of negative b is equal to I times the square root of b. In other words, when you deal with the square root of a negative number b, then the negative comes out of the square root as I, and then you have the square root of b left over, and then whatever the b is, you have to work with it to simplify it. Let's look at some examples. Example 1. Simplify the following. Part A is the square root of negative 16. I'm going to do this the long way first, and of course you can take shortcuts once you get familiar with this. Using that rule we just talked about, it's the square root of a negative number. So the negative comes out as I, and then you take the square root of the positive number that's left over. The square root of 16 is 4, so this is 4i. Of course, from now on, you can do this in one step. The square root of the negative part makes that an I. The square root of 16 is 4, and off you go. Let's look at part B. The square root of negative 12. The negative comes out of the square root as an I, and that leaves me with the square root of 12. Square root of 12 can be simplified. If I write 12 as 4 times 3, I can take the square root of the 4, and that's 2, but 3 is prime, and I can't take the square root of primes, so it's 2i square roots of 3. The 3 stays on the inside. In example 2, we want to simplify the square root of negative 8 times the square root of negative 45. So I'm going to start by rewriting the problem. The first square root has a negative in it, so that turns into an I. We have the square root of 8 left over, times the square root of negative 45. That negative also comes out as an I, leaves the square root of 45. The two i's can be multiplied together. That leaves I squared in front. And then the square root of 8, I can rewrite that as the square root of 4 times 2, a perfect square and then a non-perfect square on the inside. And also the square root of 45, I need a perfect square and a non-perfect square. That would be 9 times 5. Next, from above, we know that I squared is equal to negative 1. Then I can take the square root of 4, that's 2. I cannot take the square root of the other 2, so that stays on the inside. On the right side here, I can take the square root of 9, that's 3. But I cannot take the square root of 5. And then, in our last step, to clean things up, we multiply the numbers on the outside of the square roots. So negative 1 times 2 times 3 is negative 6. And now we multiply the numbers on the inside of the square roots. Square root of 2 times the square root of 5 is the square root of 10. As a bit of a warning, let me show you what not to do. You might be tempted to multiply inside the square roots first. And have the square root of negative 8 times the square root of negative 8 times negative 45. And that would be the square root of 360. The square root of 360 simplifies as 36 times 10. The square root of 36 is 6, and then of course the root 10 stays. But notice these answers are different, and the one on the left is the correct one. You have to handle each individual square root that has a negative first, and you have to create the I before you can combine square roots, like on the right side. That leads us to complex numbers. So what are complex numbers? Complex numbers are numbers in the form a plus bi, where a and b are both real numbers. We have a couple of extra definitions to go with this. We have the real part, and the real part is just the a by itself. And then we have the imaginary part, and that's the b by itself. It does not include the I. Now, one thing of note is that this whole thing, a plus bi, represents one number. Even though it looks like it's the sum of a couple of parts there, it's a complex number. It's one complex number. Let's look at some examples of writing complex numbers. Example 3, write each expression as a complex number, a plus bi. So in part A, we have a 5. Well, to explicitly express this as a complex number, we need the imaginary parts as well. So this is 5 plus, and there's no i's, so we write 0i, 5 plus 0i. If you have a number that's a complex number, but it has a 0 for the imaginary part, then we call those real numbers. As a side note. Part B, 36i. Well, we have the imaginary, but we're missing the real part. So we put a 0 in for the real part. So it's 0 plus 36i. When you have one that only has the I and no real part, we call that pure imaginary. In part C, we need to split this fraction up. So we're going to divide the 7 into both the 3 and the 5. So we get 3/7 plus 5/7, and the I gets tacked on there on the 5/7. So you have a real part of 3/7, and you have an imaginary part of 5/7. And in part D, we need to simplify the radical first, the square root. So the square root of negative 2 is I square roots of 2. 2 is prime, so nothing more to do there. the square root of 3, nothing to do there either. Then I'm just going to rewrite this to make it look more like a complex number. The root 3, square root of 3 part, that's the real part. The imaginary part is square root of 2, and then we tack on the I. To look at how to perform operations with complex numbers, we first need to understand the structure of when we take I and raise it to different powers. So let's go ahead and create a list of these. We'll start with I. Of course, I is equal to I. No problem there. And we already know the next one. I squared from the top of the first page. That's -1. What about I cubed? Well, I cubed can be broken down into I squared times I. And we know these two. They're right above here. So that's -1 times I, which makes -I. What about I to the 4th? Well, I to the 4th is I squared times I squared. And from above, those are -1s. So -1 times -1 is +1. Let's keep going. Do some more of these. What about I to the 5th? Well, now I can break things down with the I to the 4th. Since that is equal to 1, that's a very convenient number to work with. So we're going to go with I to the 4th times I. That would be I to the 5th. Well, I to the 4th is +1, and then times I. So I to the 5th is actually equal to I, the original I itself. What about I to the 6th? Again, if we split off I to the 4th, that leaves I squared to make up the rest of I to the 6th. We pick I to the 4th again because it's equal to 1. Easy to work with. And then I squared is -1. 1 times -1 is -1. Well, that's the same as I squared. What about I to the 7th? Again, we split off I to the 4th. So it's I to the 4th times I cubed. It's 1 times -I, which is equal to -I, which is the same as I cubed. Hopefully you're seeing the pattern here. And then I to the 8th is I to the 4th, and I'll write it differently this time. It's I to the 4th squared. So it's 1 squared, which is 1, which was the same as I to the 4th anyway. And so there you see the complete pattern. And the pattern is, and it repeats every 4 exponents. It starts off with I, then it's -1, then -I, and then +1. Now, if we look for a simple way to figure out how to determine which I or 1 or -1 it's going to produce, all we need to do is look at the remainders when we divide by 4. If we take the exponent, divide it by 4, and it has a remainder of 1, then I to that power is going to be equal to I itself. If we take the remainder when we divide the exponent by 4 and we get 2, then that I to that power is going to equal -1. If the remainder is 3, we get -I. And if the remainder is 0, then we get +1. Let's take a look at some examples. Simplify each of the following. So if we have I to the 23rd power, let's take 23 and divide it by 4. That would be 5 with a remainder of 3. So So we're only looking at the remainder. We don't care what the quotient is. What this tells us is that I to the 23rd is the same thing as I cubed, and we know from the first part of our chart that I cubed is negative I. Then we have I to the 41st power. Take 41, divide it by 4. That's equal to 10 with a remainder of 1. So therefore, I to the 41st power is the same thing as I to the first power, which is just I. Then I to the 2014 power. 2014 divided by 4 is 503 with a remainder of 2. So I to the 2014 power is the same thing as I squared, which is negative 1. Now what about i's raised to negative powers? Here I'm going to use a different trick. What I'm going to do is I'm going to add a multiple of 4 to the exponent that's given. Now I can add any multiple of 4 I want, but I'm going to choose the one that makes the sum of those two numbers just slightly above 0. So what number should we add to negative 13 to make that just slightly positive? That's also a multiple of 4. Well, the answer is 16. So I'm going to add 16 to the exponent. Now, the reason I can add multiples of 4 is because we know that I to the 4 is equal to 1. And if I take any multiple of that, let's just call it n, then that is equal to 1 to the n, which is still 1. So adding these multiples of 4 is essentially multiplying by 1. I'm just choosing a very convenient form by which to multiply. So I to the negative 13 plus 16 is I to the third, and so I to the third is equal to negative I. Let's do the same thing on part E. We have I to the negative 98. So what multiple of 4 is just slightly larger than 98? It would be 100. So I to the negative 98 plus 100 is equal to I squared, which is negative 1. You can also add, subtract, multiply, and divide complex numbers. Let's look at examples of those. In example 5, we have two complex numbers and we want to add them together. Adding complex numbers works just the same as if the I were an x or anything, any other type of variable. You just add the like terms together. So here we have the real numbers 3 and 5, so that would be 8. And then the numbers that have i's, 2i plus 1i is 3i. That's it. In example 6, we have subtraction. Works almost the same way. You just distribute the negative first. So we have 4 minus 9i. Distribute this negative to make 3 minus 7i. Then combine like terms. So 4 plus 3 is 7. Negative 9i minus 7i is negative 16i. In example 7, we have multiplication, and it works just like multiplying any other type of polynomial. So we have 2 minus 3i times 5 minus 2i. I'm going to take the 2 and distribute that to the second complex number, 5 minus 2i. Then we'll take the negative 3i and multiply that by 5 minus 2i. Next, we distribute the 2, so we get 10 minus 4i. And then we distribute the negative 3i to get negative 15i plus 6i squared. In the next step, I'm going to take 2 steps here. I have 10. We have the i's, negative 4i minus 15i. Together that's negative 19i. And then 6i squared, I'm going to change the I squared into negative 1. So we have 6 times negative 1. Multiplying the 6 and the negative 1 together gives me negative 6. And then simplifying the 10 and the negative 6 is 4, and then minus 19i. In example 8, we have division of complex numbers. Now, the trick to dividing 2 complex numbers, we need a new term, and that term is called the conjugate. So the conjugate of a complex number, a plus bi, is found by taking the middle term and switching it from adding to subtracting or subtracting to adding. So if we have a plus bi, the conjugate is a minus bi. If we had started with a minus bi, then we would end up with a plus bi. Then, to divide, we're going to multiply by the conjugate of the denominator. Divided by itself. Since I'm taking the conjugate and dividing it by itself, I'm really just multiplying by 1. So we can always multiply by 1. So the conjugate of the denominator here, 2 minus I, that's actually equal to 2 plus I. So let's start with the original division. And then I'm going to multiply this by the conjugate, which is 2 plus I. And of course divide it by the same thing, 2 plus I. And then you just work this out as if it were multiplication, and then simplify. So on top, we'll have 3 times 2 plus I plus 7I times 2 plus I divided by 2 times 2 plus I minus I times 2 plus I. And then distribute. 3 times 2 is 6. 3 times I is 3I. 7I times 2 is 14I. 7I times I is 7I squared. On the bottom, we have 2 times 2 is 4. 2 times I is 2I. Negative I times 2 is negative 2I. And then negative I times I is negative I squared. In the next simplification, we're going to add the i's together and change the I squareds into negative 1. So we'll have 6 plus 17I plus 7 times negative 1. Now notice that the 2I and negative 2I on the bottom cancel. This will always happen if you have multiplied correctly by the conjugate. In fact, that is the point of multiplying by the conjugate, to get rid of the i's in the denominator. What that leaves is 4 minus negative 1. And then we simplify. 6 plus 17i, 7 times negative 1 is negative 7. 4 minus negative 1 is 4 plus 1. And then we have 6 minus 7 is negative 1 plus 17i divided by 5. And then write that as a complex number by splitting the 5 up over both parts. It's negative 1/5 plus 17 over 5